Well, howdy, everybody. My name is Steve Macenski, and I'm the owner of Open Navigation, and we're the company behind the ROS2 navigation stack, or Nav2. I've been leading this project for the last 6 or 7 years or so if you're familiar with mobility in the ROS ecosystem, you've probably run into me at some point somewhere along the line. And I also sit on the ROS Technical Governance Committee. Today, I did want to give you a quick look at a 10,000-look view about Nav2's design, power, and how you might be able to use that in your various businesses. But then we're going to talk about some illustrative use cases of Nav2 in the wild, powering various industry leaders in a bunch of different domains. But throughout this talk, I'm going to be showing you mostly videos of real robots running our technology in deployed environments today. So all the robots you see here in this video and elsewhere in this presentation are all real robots that are really deployed today running Nav2 in a production environment. Open Navigation's mission is to support the mobile robotics ecosystem by creating accessible, professional quality robotics algorithms, systems, and tools. We think that the robotics future continues to be accelerated with democratized access to fundamental technologies that we as an industry share and then harden from our respective experiences to drive all of our success. The recent histories between ROS, Navigation, MoveIt, OpenCV, and the various AI libraries over time, I think, has proven this point over and over again. But really the only question is how we can financially support these ecosystems to be healthy. Towards that end, Open Navigation offers support services and company partnerships around ROS2, Nav2, and various mobility technologies. But a very key tenet of Open Navigation is that we are user-supported to develop and maintain the open source robotics infrastructure for the long-term future via a sponsorship model. So our sponsoring partners receive a number of added benefits, including prioritization of the project, access to engineering talent, marketing, and more. So first, I want to give you to talk a little bit about Nav2 itself, and then what that can be providing to you in your various businesses. Nav2 is the world's most deployed autonomous mobile robotics framework. Today, it's already being used by 200 companies worldwide to power everything from warehouse automation, autonomous tractors, last-mile delivery, home robots, and much more. Nav2 makes it easy to reliably and efficiently deploy robotics technologies so that users can focus most of their energy in building product applications. Less some application-specific refinements, which Open Navigation could be called to help on, but also your companies can work on as well. It is already today the industry standard, and it's built completely in the open under permissive licensing, so you can use this in your projects today for free. It's really towards the mission of democratizing access to this robotics technology. Nav2 is redesigned from the ground up from the ROS1 navigation stack with flexibility and extensibility in mind. It is centralized around the BT Navigator, which hosts a runtime configurable behavior tree, which specifies the robot autonomy logic. It orchestrates a series of these individual task servers, which perform individual components of autonomous navigation. So these are things like planning, control, smoothing, docking, teleoperation, and so forth. Each of these modules then hosts a map of plugin-based algorithms, which can be configured for your applications. Nav2 is modular, which allows you to take what you want and leave what you don't. And we do actually have many users which just take individual components of Nav2 that they would like to use for applications. But it's also extensible, which allows you to easily create additional task servers and then use them in your application within the BT Navigator and extend Nav2 for your various needs. The BT Navigator receives a mission for the task dispatcher or other type of autonomous system to perform, and then provides feedback along the way regarding that status, and then finally a result at the end about success or fail, with some additional kind of metadata that you might want to use. It also includes what I refer to as the velocity post-processing pipeline, which includes velocity smoothing to ensure that trajectories that are being executed are dynamically feasible, as well as a collision monitor to ensure you have some low-level collision checking for final outputs before executing that on the hardware. Nav2 also provides a very large library of state-of-the-art algorithms and a broad set of behaviors to support essentially every type of commonplace robot configuration and behavior. So these are things like model predictive control, the dynamic window approach and pure pursuit. We have path planners for holonomic and arbitrary non-holonomic constraints through state lattice planning and hybrid planning, as well as fusing any manner of sensor data into the environmental models, which are being utilized by the various planning and control algorithms. Very briefly here, without going into too much detail, I just didn't want to introduce the idea of thinking about autonomy as a behavior tree. While this is not particularly new in some fields, it is new to many in the robotics space even today. So this behavior tree outlines what I would think of as a realistically complex navigation behavior with 4 major stages. So the first stage here is to undock or dock the robot. So if you have an AMR platform executing tasks in a very large environment, you need to have this robot charging over time so you can have a continuous solution uptime. So stage 1, let's undock from our docking station. Stage 2, we then want to compute a path to the goal. And so this is executed either when the path is or the goal is updated. We also do so periodically to refine that path as long as we're not approaching the goal itself, which can kind of help with some jitter towards the end of the path. And then as well, we update it if that path becomes critically invalid due to collisions. We then smooth this path considering additional system dynamics and behavioral constraints. Next, and usually finally here, we then follow this path. And in this behavior tree, we follow it immediately, as long as that path is not sufficiently longer than previous paths within the same mission. Else, that usually represents that we have some sort of temporarily blocked corridor, and it's actually better for us to just wait a few moments and then try again. And then we repeatedly take this, this node that's under the planning control pipeline block, and basically until we've completed our mission. If for whatever reason both planning and control continue to fail, then what we'll do is it will clear our environmental models, wait a few moments, and then try again. If for whatever reason that continues to fail, then we'll actually back out the last few commands to get us back into a previously known navigable state, and then we can continue to navigate from there. But this is just one example of a reasonable autonomy behavior. Nav2 allows you to specify any type of behavior tree for your various needs that you need for your particular applications. Battery included, we also provide you with 60 plus behavior tree nodes, which utilize from many common types of operations. If you can't find what you need, these are all plug-in based, so it's very easy to add additional behavior tree nodes to integrate with your particular servers or create the different types of behavior that you're looking for. Nav2 provides a wider range of quality capabilities that you can choose from. This includes state-of-the-art and proven algorithms, so we support already today, out of the box, model predictive control, reactive trajectory planning, and even geometric path tracking, which is surprisingly still useful for a number of industries that we interact with. Its algorithms also consider holonomic and arbitrary non-holonomic constraints, as well as dynamic feasibility constraints. And we can fuse really any type of sensor data that you're interested into the system for planning control. So things from 3D LiDARs to 2D LiDARs, depth camera, stereo camera, IMU, GPS, AI, and even various radar sensors. We also provide you plug-in based navigator APIs so that users can specify how you want to interact with the stack yourself. So we provide navigators out of the box for point-to-point navigation. So if you're here and you'd like to go there, there you go. Kind of the standard navigation system. We also have navigators for navigating with intermediary pose constraints. So that's not just a goal point, but in some points along the way that we'd like to execute on our path, as well as full kind of coverage planning, like something like a Roomba might be interested in. But again, these are all plug-in based, so you can specify how you want to interact with the stack. But for many kinds of operations, point-to-point navigation and navigating through various pose constraints is kind of the basic primitives most people use. In terms of features, we have autonomous docking and charging, so we have continuous solution uptime. This was actually added in the last few months in partnership with NVIDIA. We also have behavioral primitives, waypoint following, and teleoperation, so you can compose those kind of basic primitives into your larger autonomy system. As well as that velocity post-processing pipeline, which helps reduce hardware fatigue, feasibility, and increase the safety of your system. We also allow you to interact with this over C++ most natively, but also there's a Python 3 wrapper around most of the task servers you can utilize as well. I think it's also worth noting that Nav2 is reasonably high quality, especially for a lot in the robotics space. So we have 90% unit integration and full system test coverage, which is frankly better than most robotics companies I've worked with in the past, and rivals that of the test quality of DDS and ROS2 itself. We also support great documentation at nav2.org that includes things like configuration guides, tutorials, getting started guides, concept explanations, examples, and a lot more. We also have professional support available either through Open Navigation or others in our kind of ecosystem, as well as the project itself continues to be professionally maintained to manage issues, fixing various bugs, performing regular releases, and then just general improvements on the framework. It's already being used today by 200 companies globally with 270 individual contributors, meaning that we have extremely active development with new features being added on a quarterly basis. It's already also been shown today to work very well on differential drive, omnidirectional Ackerman steering, articulated robots, indoor robots, outdoor robots, legged robots, arbitrarily sized robots. I mean, really, if you can name a mobility platform, there's probably somebody either using Nav2 on it today or has attempted to use Nav2 successfully. All right, well, I want to spend the remaining time here talking about a few illustrative case studies of folks that are deploying Nav2 in production. So these are companies that have been gracious enough to allow me to openly discuss some of the specifics about their solutions to you publicly. So the three that we're going to be discussing here today is a large indoor AMR logistics robot, a small urban outdoor delivery robot, and a company that's automating several pieces of massive outdoor industrial equipment. So the first here is Dexery, and they build this inventory warehouse management solution. They use this very tall boomed robot that takes data to analyze to track the efficient use of warehousing space. As you can see, this is very large. It is a differential drive base, and it's primarily in this kind of like classical robotics logistical space. But it's about 650 kilograms, 15 meters tall when fully extended, as it is most of its use case, and thus has a lot of inertia while it's moving and requires real consideration about its dynamic constraints. It's also non-circular, as you can see, obviously, and operates in these highly confined aisle settings, requiring feasible path planning to fully consider its large footprint whilst reorienting its sensor stack. This robot is also fully bidirectional, allowing it to move both forward and in reverse without preference for direction based on the orientation it needs to capture whatever data it's currently interested in. And all this has been made possible using Nav2's algorithms and technologies that are available to you out of the box today. So Dexter and Open Navigation have partnered to make the MPPI controller and the regulated peer pursuit controller fully bidirectional should you choose. So you can go forward only, you can prefer forward and go to reverse when absolutely required, or have no preference for direction whatsoever to support these kind of applications. They're also using the SMAC Planner Hybrid A-star for feasible routing across both the confined aisle settings as well as the open warehouses, considering rotations and the direction inversions required to reorient and sensor stack. The trajectory planning algorithms they use have very slow acceleration and deceleration profiles, aided with the collision monitor and velocity smoother to ensure they have very smooth and safe robot motion when moving the 650 kilogram robot at its full speed. In terms of sensors, it has primarily 2D and 3D LiDARs that are being fused in simultaneously. I believe there's 3 of each. And this is being navigated safely across multi-million square foot warehouses and 3PL locations all over the world today. But I think the major takeaway from this case study is that Nav2 is mature for very large-scale, large robot navigation. The next robot I want to talk about here is KiwiBot. So they are an urban last-mile delivery robotic platform that is delivering food and goods across cities and college campuses all over the world. So they navigate in these outdoor urban terrains in this very friendly-looking Ackerman steering platform. It employs RTK-corrected GPS, 2D LiDAR, and 3D LiDAR in order to position itself in a variety of environments more accurately than would be possible with GPS alone. That refined positioning is then ingested into Nav2 via TF transformations in order to navigate and control the robot. These sensors, as well as their stereo sensors, are then processed into Nav2's perception model for then navigation and control. They've made a lot of use of Nav2's extensibility nature by creating a number of custom add-ons for their particular domain environment. So for example, they've created custom behavior trees within Nav2's BT Navigator to define their own autonomy logic in order to be social around people in a kind of a sidewalk setting. They've also created Nav2 cost map plugins for AI-based semantic segmentation and obstacle detection. So they define classes like streets, sidewalks, grass, off-road, and more to define some navigable spaces as having higher priority than others, or other spaces as being unnavigable entirely. They also then detect cars and people and the other kind of usual objects that you'd expect, and then marry these AI-based detections with their depth and LiDAR-based detections to feed that into the environmental model for avoiding collisions. KiwiBot uses the environmental model that Nav2 provides alongside our perception algorithms with their AI-based customizations that are fed into the SMAC Planner and the MPPI controller. These provide KiwiBot with highly dynamic social behavior that fully considers the robot's non-circular, non-holonomic kinematics while moving at high speeds. And this solution is already today deployed across college campuses in cities like Berkeley, the University of Maine, San Jose, and 30 others globally. The main takeaway, I think, for this case study here is that this is a canonical example of what was not previously possible in ROS1 navigation. This is not an indoor 2D-based, LiDAR-based circular robot. Nav2 is completely new and is far more algorithmically, behaviorally, and architecturally mature to support a much broader range of modern applications, and this includes outdoor and urban environments. And this has really all been made possible by the development in the last 6 years of the community, myself, as well as Open Navigation. All right, the last here is Polymath Robotics. Ilya was on the last panel. Woo, yeah. They provide these easy-to-use, out-of-the-box autonomy for heavy industries. So they provide standard API calls for autonomy on a variety of equipment to automate the world. The majority of their customers are in these outdoor semi-structured-like environments, so think things like mining, agriculture, construction, maritime, and other kind of large-scale heavy industries. Due to the variety of autonomy capabilities that they provide, they rely on a variety of different localization algorithms depending on the application and need. The vast majority of their customers have very large multi-ton pieces of equipment with complex drivetrains. So for example, they use Nav2 and support multiple customers with articulated Ackerman dynamics. However, they have many different classes of robots with a wide variety of characteristics that they support. The Nav2 framework and algorithms are being leveraged across all of these different applications, in addition to Polymath's custom integrations. So for example, they've recently created a cost map plugin layer for tracking, for processing radar tracks in order to avoid high-speed dynamic obstacles in their scenes. So this cost map layer has actually been recently open sourced, is the subject of a ROSCON 2024 talk in just a few weeks here. So if any of you are going to be in Denmark, I definitely recommend checking that talk out. But overall, Polymath Autonomy leverages Nav2's SMAC Planner, MPPI controller, regulated peer pursuit controller, behavior tree navigator, and general software framework. But that's in addition to their custom behavior tree nodes, behavior trees, teach and repeat routing, and much more that power their specific customer requirements. The main takeaway, I think, from this case study is that Nav2 is suitable for heavy industries, not just indoor logistics AMRs, not just small outdoor applications. It really can handle an extreme diversity of different equipment types and formats. Yeah, and Nav2's use cases aren't just limited here. We have 200 plus companies worldwide that use it in a variety of industries: agriculture, inspection, logistics, research, delivery, data collection, hospitality, hotels, construction, mining. Really anywhere you can imagine mobility technologies being deployed today, I probably partner with somebody or I'm aware of somebody using this in their production environment. Interestingly enough, we actually have a couple of boats, a couple of large-scale drones, and even a couple of urban outdoor autonomous driving use cases, although I highly do not recommend that. But these are companies that are 5, 10-person startups, some of which are here today, as well as companies all the way up to Fortune 500 business units and everyone in between. Nav2 is supported and made possible by our sponsors. So these are companies that partner with Open Navigation to develop and maintain Nav2 and its associated open source robotics infrastructure for the long-term future. This is made possible to perform daily maintenance, strategic development, bug fixing, releases, documentation writing, and so on that would not be possible without their support. In exchange, they receive roadmap prioritization, active support, regular consulting meetings, and other types of benefits similar to that. If you're already using Nav2 for a various product or service, a sponsorship is a great way to make sure that you continue to receive a great platform with new updates to advance your business, as well as having expanded influence and access to the project. So I'd like to thank our sponsors that help us out with all this stuff: Dexery, NVIDIA, Stereo Labs, and Polymath Robotics. If you're interested in learning more about how to sponsor Nav2 or partner with us, please do find me after this talk. All right, in closing here, we're still looking for a couple more project sponsors, so give me your money. But in addition to that, we also offer corporate partnerships and support services. So we'll work with your team to develop highly robust and specialized robotic systems that meet your solution needs. Here you can find some links to the software on GitHub, as well as our documentation at nav2.org. And I think that about wraps things up, so thanks for your time.